ladies and gentlemen, class recording has started. So, in the last outline, we drew our big picture of a bunch of orbitals, right? And hopefully you're at the point right now that orbital, by definition, is a likely place where we find electrons, or a high probability of finding electrons. And that the idea of an orbital is based off the work of Heisenberg and Schrödinger, Heisenberg's uncertainty principle, that says we can't know where and how fast an electron is going at the same time, like one or the other, but you can't know both, right? And then Schrödinger came up with the idea of mathematically representing the location of electrons based on where they've been in the past, and that's what we call an orbital, blah, 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 blah. Okay, good there? All right. So, orbital filling. Just because all of those orbitals exist doesn't necessarily mean we find electrons in all of them, all right? So there is one sort of overarching rule that governs where electrons go first. What did we call that rule yesterday? Anybody remember? What is the rule that we use to sort of determine where electrons go first and where they go second? Hund's rule is more about spreading things out. Nope, the other one. Okay, the off-bow principle. All right, there it is. So, off-bow principle essentially says what? Sam, good. We fill up orbitals from lowest energy first to highest energy last, right? And so we have this chart here that represents essentially the off-bow principle that shows us which orbitals are the lowest energy, which ones are next lowest, et cetera, et cetera, et cetera. And we talked about the idea that when we're reading this chart, on the left-hand side it says increasing energy of electrons in orbitals. That means we're going to read this chart from bottom to top. You are going to get this chart on your test. Okay? You do not have to memorize it. It will be available to you on your test. So obviously we've been using it a lot. We used it a lot yesterday. We use it a lot today. But you don't have to memorize the order that they go in. Okay? Good? All right. So we said that an orbital diagram represents where electrons are in the atom, right? Shows the distribution of our electrons within the orbitals that actually exist. We don't actually draw the shape of the orbitals, right? We draw a representation of an orbital either through a circle or a box or a line and stuff like that, right? We said before we draw our orbital diagram, what essential piece of information do we need to know about the atom that we're trying to draw the orbital diagram for? Number of electrons, because if it's a drawing that shows us where electrons are located, we have to know how many electrons we're working with, okay? All right, are we going to jump right in here? Do you want me to jump right into something? All right, okay. All right, so on your sheet, page 2, okay, we drew orbital diagrams up through carbon, okay? Down at the bottom of the page, you have neon that's sort of blocked off, and then you have some space down underneath neon on your outline. In that space underneath neon, all right, I would like you to draw for me, okay, so this is sort of an additional one. I would like you to draw for me the orbital diagram for oxygen. Okay? So in that little space down at the bottom of page 2, go ahead and draw me the orbital diagram for oxygen. Feel free to discuss with the person next to you if you would like to. All right? Or if all of your friends love it. You could turn around and do it like you. So while you guys are doing that on your outline there, I'm going to do it up here on the board, okay? Are each of those orbitals full yet?
No, because each of would be said if you have two.
Right, but okay. This is good. No, it's good. Okay? This is a good discussion. Okay? All right, so. All right, so up on the board, I have drawn an orbital diagram for oxygen. I've gotten through the first 4 electrons. What I'm going to show you right now, I would never be able to tell on the test whether you actually do it this way or not, but to be consistent with the rules that we follow and stuff like that, I'm going to draw it in the following manner. All right, off-bound principle says we fill orbitals from lowest energy to highest energy. That's why we always start at 1s, because it's the first one that we come across. It's closest to the bottom. It has the lowest energy. The next one we come across is 2s, right? But in both cases, how many electrons can each of those orbitals hold? 2. And that's why I filled up the first 4 like this. But then the next ones we come across are the 2p orbitals. Okay? We talked about the idea that there are 3 orbitals that are labeled as 2p, one on the x-axis, one on the y-axis, one on the z-axis. But right at the end of class yesterday, we introduced Hund's rule. And Hund's rule says that if we have orbitals that are evenly spaced out energy-wise, electrons will try to spread themselves out as evenly as possible within those orbitals. So, when I'm drawing, this is, if we're going to be consistent with Hund's rule, this is how we would draw it, although like I said, there's no way that I would be able to tell on a test whether you were doing this or not. Okay? So, here's electron number 5. Okay? Where would electron number 6 go? In the next orbital, right? Even though this orbital is not full, if given a choice, this electron will not go into that orbital. It's trying to spread out as evenly as possible, because what are all electrons trying to do to each other? Repel each other, right? And so that means electron number 7 would go here, okay? But oxygen has 8 electrons, right? So we still have 1 to go. Now, would that next electron jump up on this chart at the bottom of the page? No, because are these orbitals full yet? No. They are not. So even though there's already an electron in each of these orbitals, pairing up with another electron in this orbital is less energy than jumping up to the next orbital on the chart. Okay? Yes, but the repulsion of the two electrons in this orbital is less energy than jumping up farther from the nucleus to another orbital, right? So, so we kind of talked about, like, this is a p orbital, right? Even within this orbital, can the electrons stay away from each other? Yeah, like one could go over on the yellow side and one could go over on the red side, right? So even within this orbital, they still have the chance to be far apart from each other, okay? And that is less energy, like I said, than jumping up to a completely new orbital, okay?
So if there were like three more electrons,
okay.
won't they all be
So hold on 1 second to that, okay? But to finish this off, we have one more orbital to place, or one more electron to place. Does it matter where it goes? In this case, no, because all 3 of them already have 1 electron, so it really doesn't matter where we put the second one, okay? Or sorry, where we put the 4th one, right? Most books are going to put it right here, but putting it there or here would be just as right, okay? Good for oxygen. Okay, now, if the next one at the bottom of the page, which would actually be right above this, right, that's neon. Neon has 10 electrons, right? I'd go here first, 1s. I'd go here second, 2s. And then the next set of orbitals that I come across are 2p. Okay? I have to place 6 electrons here, right? Again, there's no way I'd be able to tell whether you did this on the test or not, but 5, 6, 7, 8, 9, 10. Okay? Good there? All right. Are those orbitals full? Yes. So the next one that we come across, the next element we come across is sodium, right? Which I believe is at the top of page 3, yes? Right? Okay. Oh, okay, so sodium has 11 electrons, all right? Meaning the first 10 are going to do this, right? But now we've completely filled up that 2p level. So now that all of the 2p orbitals are completely full, now we go back to the chart and go, okay, where do we go next? And what's the next, the lowest energy orbital that we come across?
3p.
Not 3. Well, 3s is closer to the, so Gary, even though it's one column over, right? 3s is closer to the bottom than 3p is, right? So 3s is going to be the next one that we go to, right? So that means here, if we're going sodium, right? 11 electrons, 1s, 2s, 2p, all right, and then I'm going to go to the next lowest orbital on my chart. That's labeled as 3s. And then we're going to go there. Okay? Good? Okay? All right. So the little note there at the bottom, or the little note underneath sodium on your outline, says noble gas notation. We're only up to element number 11 on the periodic table. Right? And this is already starting to get a little bit long and a little bit unwieldy. All right? So we can use notation to help us shorten this up a little bit. That still represents what we're talking about, but now we don't have as much to write. Okay? If we take a look at the beginning part of this notation, right? It looks real similar to this one. Yeah?
Yeah.
Okay. Good. Glad we see that. Okay. So, what we can do is we can use a shorthand notation to represent everything that has happened up until a certain point, and then just pick it up from there. Okay? So, with this one, everything in the box, we can shorthand represent by putting the symbol for neon within these square brackets, and then pick it up from there. Okay? Right. But, Grace, this here, right, when we put neon in here, how many electrons are we, so neon has how many electrons? 10, right? Because that's neon's atomic number. So when we put neon in these brackets right here, what we're essentially saying is that the first 10 electrons that we come across are essentially going to be exactly matching neon. And then we just pick it up from there. Okay?
So if we wanted to, and when we were doing the forum,
Yep.
we technically put lithium in the beginning and then go on?
No. Okay? Because here's why. When we have neon, right? What's true about all of the orbitals that we have come across so far? They're all full. And more importantly, right? More importantly, because here, okay, so here, technically, when we do boron, these are all full too, right? But there's something different about these ones being full and about these ones being full. here, the two p's are full, and what does that mean about all of the 2 orbitals? They're all full. Every orbital that starts with a 2 is completely full. Okay? That means we got to jump up to the next level. What we find is that the elements that are in column 18 on your periodic table, the one on the far right, okay, we have levels that are completely full. And we can use them to represent a certain number of electrons up until that point, and then pick up our orbital diagrams from there. Okay? But only elements that have full levels, like the ones that are on the right-hand side. Okay? Good? Okay. Nothing does that answer your question? Okay? Mo, go ahead. Good. Yes, that can work for helium or neon or argon, right? Or krypton or xenon, right? So here, let me jump ahead a little bit, okay? Don't think it's the next one, but a little bit farther down on your page, I think we come across potassium. Yes? Okay? All right, so let's talk about potassium, because we can go 2 things here, okay? First, I'm going to do the whole deal, and then I'm going to do shorthand. All right, so we look on the periodic table, we find potassium. How many electrons do we have to place? 19 electrons. Okay. All right, so if we're going through this, right, we start off on 1s, 2 electrons there. Next we go to 2s, 2 electrons there. Well, let's do the whole thing first, okay? I know it's really long, but I want to make sure that you understand where we're going with this, okay? All right, so then, oh, wrong color. 2p, all right? 5, 6, 7, 8, 9, 10. Okay, next one we come across is 3s. 2 electrons there, that gets us up to 12. Okay? So then, next one on the chart that you come across is 3p. As you're moving up from bottom to top. Okay? Nope, 3p, sorry. 13, 14, 15, 16, 17, 18. Okay? So, first, following the pattern to finish off this electron configuration, are all of the 3p orbitals completely full? Yes. They are. So we go back to our chart, and we go up from bottom to top. Even though there are some 3d orbitals, which is the next closest orbital to the bottom of the chart? 4s, right? Once we get past the 3rd level, because there's a lot more space, we find that the 4s and the 3s start kind of mixing together, and up here, like 5s and 4s and 6s end up mixing together. Follow the chart, all right? So the next orbital that we would draw would be 4s. And how many electrons need to go in that 4s orbital? 1. There's our 19, okay? But, like we just talked about, okay, to get to 19, you have to go through 18. Okay? And so, the first 18 electrons that we placed in these orbitals look exactly the same as the orbital diagram for which element? Argon. So we can replace these first 18 elements, or sorry, 18 electrons, by putting argon in square brackets, and then we just pick it up from there. Okay? How's that?
It's good.
Good. Everybody else? All right. So that's where we can start making shorthand work of this. Okay? All right, the next one, right underneath potassium, I think, if I remember correctly, is manganese, yes?
Yes.
Okay. So, manganese. Be careful because there's a manganese on the periodic table and then there's a magnesium on the periodic table, all right? I want this one to be manganese, all right? So, manganese, you have to figure that out first, right? Okay, you find it? Okay. All right, so, Connor, now that you found it, how many electrons does manganese have? 25. All right, I want you to either by yourself or with the person next to you come up with an orbital diagram for manganese. Either a full orbital diagram or using the noble gas notation to make it shorter. Go. All right. So, up on the board. There we go. All right. So, up on the board, there's your two options, okay? The top row would be the full electron configuration, and then the bottom row would be using noble gas notation to shorten it up, all right? Next one that we found after, or the next one that shows up on the chart after 4s is full is 3d, right? Here's 4s, the next one up is 3d, okay? But just like the chart shows you, how many 3d orbitals are there? There are 5 of them, and they are all the exact same height up from the bottom, meaning they all have exactly the same energy. Which means once we start filling them up, we have to spread them out as evenly as possible before we start doubling up. Good? Yes? No? Or maybe? Okay. All right. So the last page of your outline talks about electron configurations. Orbital diagrams are a shorthand way of representing where electrons show up in that big picture that we drew on your previous outline. Electron configurations are a shorthand way of representing what an orbital diagram tells us. So, let's go all the way back to hydrogen. Okay? As far as an electron configuration goes, not as detailed again, a shorthand way of representing it. So, when writing an electron configuration, we start off with writing the orbital name that we used, okay? No circle, no line, no box, just a 1s, okay? And then we use superscripts or exponents to represent the number of electrons in that orbital. So here, for hydrogen, it only has one electron, and that one electron is in the 1s orbital. So the electron configuration for hydrogen looks like this. When we're reading it, we don't say math terms, we just read the numbers and letters. So the electron configuration for hydrogen is 1s1. Okay? Then, for helium, we start off writing the name of the orbital where our electrons appear, and then how many electrons are in this orbital, Connor? 2. But this isn't 1s squared, it's 1s2. It's representing how many electrons are in that orbital. Okay? So then, if we jump it up here to lithium, right? 1s2, but then 2s1. Okay? Yeah, it's just one long yeah, there's no spaces or anything like that. We just write it in order. Okay? So far, not really that much shorthand. Okay? But when we start getting to carbon, that's where it starts getting a little shorter. So, for carbon, 1s2, 2s2, but here's where an electron configuration differs from an orbital diagram. When we have multiple orbitals of the same energy, right, in an orbital diagram, we draw them all separately. Here, we write them all together. So we're only going to write 2p one time, but then how many electrons total are there within all of the 2p orbitals? 2. So carbon is 1s2, 2s2, 2p2. Our very first one from today, oxygen, which I don't think actually shows up on your outline. Is that correct? Is oxygen on your list on page 4? Okay. So, but just to be consistent with what we're doing here, okay, because this is a good example, okay? 1s2, 2s2, but then we just grouped the 2p orbitals together. How many electrons total are there within all of the 2p orbitals? There are 4. So the electron configuration for oxygen is 1s2, 2s2, 2p4. Now, even though it doesn't show us this in an electron configuration, you need to understand that even though it doesn't say how many 2p orbitals are there in this atom. How many 2p orbitals are there in this atom? There are 3 2p orbitals. Right? And even though it doesn't say specifically in the electron configuration, you need to know because of Hund's rule that they're split up like that, right? Electron configurations are shorthand representations. They don't give you as much information, but they're based on the idea that you already know this information and we're just representing it. Okay? Good? Noble gas notation still works in electron configurations. So we can start off sodium with neon in our square parentheses. And then we can pick it up from there. Okay? And then, if we apply all the stuff we've learned, right, for manganese, so that would be the full electron configuration for manganese, all right? Does that make sense where all that came from? Okay. Again, the last part, even though the electron configuration doesn't show it, how many 3d orbitals total are there? There are 5 orbitals. How many electrons total exist within those 5 orbitals? 5. That's why we end up with 3d5. Okay? Yep. That is just as valid. Okay? Where putting argon in those brackets represents the first 18 electrons that we come across, and all of those orbitals are full, and then we just pick it up from there. Okay? Good? All right. Notice bottom of the last page, I crossed out sections of the outline. You're not going to be responsible for those sections right there. We'll pick those up when we talk about the periodic table and stuff like that. Okay? So, tonight, quiz will become active right after class today. I should say this afternoon. Quiz will become active right after class. It deals with orbital diagrams. I don't think there's actually any electron configurations on there. It's just orbital diagrams. But you will have to know electron configurations for the test. Okay? Tomorrow in class, review. If you haven't gotten yourself a objective sheet yet, probably a good idea to get one tonight so you have it in class tomorrow so that we can ask me questions if you need to. All right?